here's what happened. This is the data as happened. Now, the green over there is not going to be important for the analysis of the randomizer, because it was sort of random how I put the songs in there anyway. I called Pat Benatar song number 1. I could have just as easily, making the Excel spreadsheet, put Pat at song number 7, or 8, or 5, or 10. It doesn't matter where she goes. Well, whatever the song number 1 was, showed up 8 times. So it happens to Pat Benatar. Doesn't matter. Totally irrelevant. So, song number 2 showed up 3 times, song number 3 showed up 7 times, and so forth, and so on, and so forth, and so on, and so forth. So, that's the observed. That's what we saw from our data, and let's check math on that. That should sum to 50. I call this the observed. It's also called O in the biz. So the sum of these O, or observations, should be 50. I'm going to trust it because I had Chris shake 50 times, and I was having Excel keep track of it for us. Yay, us. Okay. What goes in the expected column? What goes in the expected column? What do you think?
What, like 5 for each?
Exactly! Thank you, Eric! That's exactly what goes in the expected. Why 5 for each? This is perfect. Good, good. Why 5, Eric? Go!
Oh, so they each happen the same amount of times?
Yes!
So I guess that's what it would be if it was actually random.
On average, that's what you would expect. This goes back to the world of the binomial. You would expect, and this goes back to whoever told me to run the z-test. Michael, I asked you which hypothesis to put in, and you said, for that z-test we just ran for Pat Benatar,
Yeah.
and you told me what hypothesis to put in as a percentage. 10%. 10% of the 50 songs is 5. So if you have 10 5s, that would also sum, the sum of the expectations is also going to be 50. Yes, love it. Now, from these 2 columns, or at least from one of the columns, we can get the hypotheses that we need to test. We can get the hypotheses that we need to test. I'm going to swing over here, because we haven't even set them up yet. We haven't even set them up yet. We can't test anything until we set hypotheses in motion, because that tells us what we're actually going to believe. We already know, the p-value was already given to you up in technology. Great, but in order to know what that means, you have to know what to look at, what to believe. Figure out next. All right. The null hypothesis. In words, what's it going to be? What do you think the null hypothesis is going to be in words? Don't worry about symbols yet. We'll get the symbols in a minute. What do you think in words? I'll get you started. The iPod's randomizer is random. Why think that it's anything else except random, right? That's the idea of the hypothesis test. The reason we're running this test is I want to see if that press release I saw 5 years ago holds any water. I want to see if that press release holds any water. Let's see if the iPod's randomizer is actually random. The alternative is going to be the iPod's randomizer is
Not random.
not random. Yes. Perfect. And that's fantastic. Except it's not. I mean, it's fantastic, but it's incomplete. Because in order to decide whether something is random or not, what do we need? What do we need? What's the problem with just leaving it like that? What do you think? Say that again. We need some kind of a value to compare it against. This is like anything else we do in this class. There's a curve. And we slide along that curve, away from average or towards average. And if you slide too far away from average, you then say, ah, something's up. Chance of type 1 error, of course. But if you slide too far away, you say something's up. We don't think that we can believe this anymore. So here's what we're going to do. We're going to use what Eric and Michael have already told me to turn this into a null hypothesis. If the iPod were behaving randomly, quantify it for me. Quantify it for me. Use what Michael said earlier. What did you say? Say it again, Michael. You said that Pat Benatar should show up
5 times.
Well, give me it as a percentage. I'll have your percentage.
Oh, 10%.
10% of the time. How about Run DMC? How about Pat Benatar? Or yes, Pat Benatar. How about Iron Maiden?
10%.
How about Anthrax Public Enemy? Every song should show up 10% of the time, yes? Which means that the percentage of time that song 1 shows up should be equal to the percentage of time that song 2 shows up, should be equal to the percentage of time, blah, 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 all the way down to the last song. They should all be equal to each other. This looks like testing for 2 hypotheses, except you've got 10 of them strung together. And if you had 20, you'd have 20 strung together. And if you had 4, you'd have 4 strung together. If they're all equal, they're all equal. Now there's also a quantifiable number attached to that since they're all equal. They should all be, as you guys said, 10%. But you don't have to list that if you don't want to, because it's a given. If they're all equal to each other, they have to be 10% each, because that's to add to 100. Is that fair? Is that fair? Good. What's the opposite of that? I've been calling it 1GPA. What's the opposite of that?
Not equal.
What's not equal? This is
The P, or I mean the number of times each song's played.
Make it more precise. I love what you're saying, Aaron. Make it more precise. Do they all have to be not equal?
No, not necessarily.
Good, good. This is where I'm going to pick on 243 again. What's the opposite of everything is equal? Use some English words before you say the word equal or not equal. At least one is different. It doesn't mean they all have to be different, but at least one has to be different. For example, if you saw a humongous spike of Pat Benatar, but you saw 7 or 9% of all the other songs, Pat would be the one that would be off, and the rest might be close enough. Might be close enough. Might be. So the trick is, verbally, it's just at least one of those proportions is off. And I'm not going to pick greater than or less than. We'll deal with that later. Greater than or less than. We're just going to look to see if it's too high or too low. Makes it a nice strong test that way. Good. Thank you, Eric, for that. Thank you, Will, for following up. Yeah, absolutely. We're just going to see if at least one. It could be more than one. Laura, ask me that question. Ask me that question.
I don't have a question.
Oh, okay. Thought you did. My bad. So, there we go. We're just going to see if something triggers, boom, something's off. Now, what I'm going to do is I'm going to walk you through the construction of how we're going to test this. We need a test statistic and a p-value at this point. We need a test statistic, and we need a p-value. The problem is, this will no longer fit any curve we currently have, unfortunately. It just doesn't fit any of the common curves that we have. It doesn't fit a z, it doesn't fit a t. But that's okay. That's all right. We got a new curve we can talk about today. He's called chi-square. You'll see why he's called chi-square momentarily. We'll come into him. Unrelated trivia to this, the Greek letter chi. Greek letter chi. You ever seen, I used to be told all the time by my mom that you can't write Xmas for Christmas because you're crossing out the name of Christ. And for years and years and years, I was like, I can't write Xmas because you're crossing out the name of Christ. And then I discovered that that's the Greek symbol, shorthand for Christ. And the whole reason Xmas came to be was a shorthand for Christmas. Christmas. Put the chi in there. Genius. Genius. I told my mom, she was not impressed. Anyway. Love you, Mom. All right, so, we need to go here. So, how are we going to put what we saw with what we expected to see and compare them? Think. You know what we have to do next. This is the one and only time we'll do this manually. Everything else we've done automatically for. But I want you to see what's going on because it's that different of a result. What are we going to do? What are we going to do? Well, that's what we saw. That's what we should have seen. What do you think?
Subtract.
Yes! Do that minus that. Next column. Observe minus the expected. See what you get. 3. Negative 2. 2. 1. 1. Negative 1. Negative 3, 3, negative 3, negative 1. Beautiful. What should we do with that? What do you think? You're in a statistics class. What would you do with a bunch of numbers?
Put it in the list.
Put them in a list and do what with it? Go ahead. Statistics. You get a bunch of numbers put in front of you, and you're trying to look for an overall characteristic of that list. What would you do with those numbers? What do you think? Shoot from the gut. What would you do?
Put them in some sort of graph or
Table. I love that. Graph, table, and then see what? Where the what of that graph is.
The center of the...
Where the center of that would be. I love when we're talking about center. Graphing and looking for a center. There's an easier way numerically without a graph. We could just take the what of these values. We could average them. Don't bother. What will it be? By definition, it has to be this, actually. It has to be 0. Because the ones that are under and the ones that are over are going to have to balance. Think about why. There are 50 numbers here. There are 50 songs represented here. And there are 50 songs represented here. This one, for example, is 3 too big. That cancels the one that's 3 too small. This one here is 2 too small, which will cancel, say, these 2 that are 2 too big. And everywhere you pair them up, they'll cancel. We had this problem back in 243, if you remember, when we were trying to measure variation. We did the differences of the data points from average, and we got done and we said, hell yeah, let's average that deviation. And we couldn't because it summed to 0. So how did we fix it back then? Do you remember? I love week 9. It's awesome. Just yell louder. How did we fix it in 243 when we got to this point? Do you remember what we did? Will? We squared the differences and dealt with that, and then we dealt with it by taking the square root later. Thank you, sir. So we square the deviations. We square the deviations. Now, of course, this produces somewhat of an unintended consequence, because it exaggerates the ones on the outside. The furthest ones get exponentially further away. The ones that are close get exponentially closer if they're less than 1. They're not in this case. But we're going to have a 9, we're going to have a 4, we're going to have a 4, we're going to have a 1, we're going to have a 1, and a 1, and a 9, and a 9, and a 9, and a 1. Now at this point, we have to default to the mathematics that has been created for us. Because at this point, I would personally do some kind of an average on that column. But I didn't write the rule book on this test. So, the construction of the test statistic takes one more term, one more column. I apologize if you're out of room, or you're close. One more column. What we do is, we take that quantity, and we divide it by the expected value that we should have gotten. Now this is weird, because this doesn't have a logical unit. Follow with me on this one. Right now, that unit is songs squared. If you think about it, it's song occurrences squared. Because you took the difference of the songs, we saw 3 too many, 2 too few, 2 too many, 1 too many, 1 too many, and so forth. By squaring that, you saw 1 squared, too many squared. That doesn't make a whole lot of sense, right? But don't worry about that. I think the reason why we do this is to get rid of that squared quantity and knock it back down to the correct unit. I think. I could be completely wrong about that, but I think that's what's going on. The history I've done on this particular test has kind of run me into dead ends. All the searches that I do dead end me into, this is what we do and here's why we've always done it. But nobody gives me a discussion as to where it comes from. I'm still looking. So what you do is you take that value and divide it by that value. So 9 divided by 5 gives you 1.8. 4 divided by 5 gives you 0.8. We'll just keep on wandering down. There's a 0.8. There's a 0.2. 0.2. 0.2. That's a 1.8, as is this, as is this, as is that. Those quantities-ish, if you think about them, are kind of like a standardized, normalized offness. That's a completely awful English statement. But when you squared the differences, you got the squared units. Kayla, go.
Shouldn't the last one be 0.2?
Yes. Thank you. Did I screw up anywhere else? You're a math major. I'm going to touch you all on math mistakes. Okay, good. We're good. So what you're essentially seeing here is the bigger these numbers are, the more off the song was. The smaller they are, the more close to what they should have been. Ideally, if they were perfect, what would those numbers be? If we had any songs that showed up exactly 5 times, they should be 0. They can never be negative, though. So what you're doing is a cumulative summing of offnesses for each song. Man, these are weird statements coming out of my mouth today. But that's what you're doing. You're keeping track of the cumulative error of the songs. This is the column we're going to sum up. Let's do it. Sum this bad boy up. See what we get. We sum this column. We end up with, let me see, I got 2. No, that's 2, 3, 4, 5. I get 8.6. Check me on that, friends. Check my math on that one. Kayla, looking at you. Can't jump in next to you. Should have told me you're a math major. You got 3 more days. Have fun with us. 8.6, check. you guys check me.
Could you say again how you got the 5 break?
Yes, thank you, Laura. Yes, absolutely. As we're checking, Kayla, you're still checking, right? This 5 here, this column right here, if you will, it's the null hypothesis column. Think about it that way. It's the null hypothesis column. And the reason you think of it that way, Laura, is if the null hypothesis were actually behaving, you should see each song 10% of the time. Which means if I run it 50 times, 10% of each of those 50 should show up for each song. There's 5.
Okay.
Is that fair?
Yeah.
Thank you for the question. You can also see now why I had Chris run at 50 and not anything less than 50. Because if you remember from back in the day, n times p has to be at least 5 in order for these tests to collect enough data to actually see patterns. So n, 50, if I knew that each p had to be 10%, I know that n times p has to be at least 5. So that means n has to be at least 50. If I ran it more times, I get better data, assuming it's quality data. Laura, does that make sense? Great question. How'd I do? Kayla?
I got
9.6? Is it 9?
Yeah.
There we go. Did you guys check me on this one? That's your test statistic. That is your test statistic. And its variable is chi-square. I'm going to swing this back over here. Hi, Mom. I'm going to swing this over here. That is your test statistic. 9.6 what? Now, the default answer that you've been using for the past 6 weeks is 9.6 what? Every test statistic has been a measure of standard deviations. This is not that. This is not that. Good. Laura's like, oh, you bastard. That was good. That was good. She popped her head up. She's like, wait a minute. That was good. That was good because everything has been standard deviations until this moment. Thank you, sister. The reason this can't be standard deviations, the reason why this can't be standard deviations is standard deviations can go above and below 0. Can this go below 0? Can that number ever go negative? It can't, because we took care of the negatives by squaring and then dividing. This is a brand new curve. This is a brand new curve. Check it out. Check it out. And this is something I'm never going to have you graph manually because it's kind of ridiculous. It's kind of ridiculous. Here she is. Here she is. Let me kill that light so you can see what's going on. This is called the chi-square goodness of fit curve. We'll come back to that in a moment. So, take a look at it. Look at the leftmost value on the horizontal axis. 0. That's because you can't go below 0. There's the function in case you're wondering. I wouldn't wonder personally, I just let it go. That's what generates this curve. This is why I've been doing historical research into this curve. I want to know who invented it, first of all, where it came from, what was motivating it. I like it. I think it's fantastic. I think it's cool. I just don't like things that fall into my lap and go here. I don't like that too much. But this is what everybody uses, so we're going to keep using it and I'll eventually find a reason for it. Probabilities are on the right side. Probabilities on the right side. Now, what I love about this curve is, oh, you can't see this yet because the camera's pointing at the wrong thing. Now it's pointing at my 5 o'clock shadow. A little bit more. Okay, good. What I love is this. What's the chance that when we sum up all those little deviations, what's the chance they sum to 0 based on this curve?
0.
Essentially 0, which means if something is behaving randomly, it shouldn't sum up to 0 because that would be too perfect. Yes? If they summed to 0, that means everything in the randomizer behaved exactly as it was supposed to be. But that shouldn't happen. That's almost too unrandom. Yes, we should get clumping. Correct? Yes. Now, as you notice, as we start getting further away from 0, what happens to the likelihoods? They start getting bigger. Exactly. Listen break, brother. Listen break. And they max out right around a value of about, what's that, about 2.5 or 3. As we get further away, they start dropping down. They start falling again. And then once you get too deviant, now you get out into this tail. So if you get too deviant, then you fall out into that tail. That tail technically go on forever. Technically speaking, it goes on forever. And that means you're wickedly deviant. So it's on 50 Pat Benatar songs and nothing else the other 9. You're way out in that tail. The question is, where did we fall? We fell at 9.6. So we fell right here. We fell right there. Now the way this test is going to shade, and I can't get Excel to do this just yet, it's going to shade to the right and add up all of that area. So what I have to do is, I have to enter in the test statistic of 9.6. Degrees of freedom is something, here we go, hang on a second. The degrees of freedom is something you might remember from back in the day. Degrees of freedom is always one less than your sample size when we talk about averages. The way this particular curve is set up, it doesn't count the sample size, it counts the category sizes. How many categories do you have? So we have 10, because there are 10 songs. You go one less from that to get 9. Don't you worry about that. I took care of this for you in the program I gave you. So our p-value, friends, is 0.38, which would mean if we threw up a vertical line right there and shaded to the right, we would have shaded about 40% of the curve. That's less than half, but who do we believe? Who do we believe? The null hypothesis, which means we believe p-value is about 40%. No, 38% in case you're checking your math on this one. What do we believe?
The randomizer is random.
We believe the randomizer is random enough. It does not appear that the randomizer is not random enough, aka we think the randomizer is random enough. Could we be wrong? Of course. How could we be wrong in this case? Type 2. I'm not even going to ask you to calculate the chance of that. It's too ridiculous with a goodness of fit test. Will, what's on your mind? You're thinking of something. You're not? Okay. I'm misreading faces. I apologize, Laura, Will, everybody else. I'm misreading faces today. I apologize. Now here's the interesting part. There's a couple ways you can be wrong with this randomizer. Check this out. I'm going to come back to this momentarily. But check this out. This right here is a random number generator generating 50 random numbers between 1 and 10. And that's the graph over there of. So this would be the exact same thing that me and Chris just did, except using Excel to just generate 50 random numbers between 1 and 10. Watch the p-values up top. 0.85, huge, yes? This is random enough. If we saw that distribution of songs in the iPod, that would be random enough. How about right now? Is that random enough? Yes, that's random enough. Is that random enough? Now check this out. That's random enough even though we did not see any social distortion. It's still random enough. That's where the goodness of fit curve shines. If we ran that as a one prop Z, it would come back, there's no way that's being random enough. It's 0 out of 50. You should see 5 out of 50. But that ignores the other 9 categories. That's where this is beautiful. Let's keep going. Random enough? That's almost the same p-value we got, 38%. Different distribution. Look, this one's heavy on Run DMC, as it should be. Now watch though. Eventually up there, oh look at that one. That's almost, it looks almost the same. We lost a song. Look at the p-value. It's getting very small. We eventually should get a p-value that's less than 5%. So that came on real quick. I shouldn't have to wait that long for it. How often should it happen, friends?
There it is.
How often should it happen? On average, false positive.
5%.
5% of the time. 1 in 20 trials it should happen. And that happened roughly after 20 hits of the F9 button. I'm not saying it should have happened after 20. That's on average, yes? Look at that. That is not random enough. And you can see why. Too many deviations summed together. These guys are too little. These guys are all too tall. We had a couple too talls, but they weren't that tall. And the littles that we had weren't comparatively that extremely off from 5. Yes? That would be a false positive. Because these numbers are being generated randomly. And we still got a small p-value, false positive. Happens 1 in 20 times. False negative, I can't test with Excel. Why can't I test the false negative with Excel? Can anybody think of the answer to this? It's a tricky question. Why couldn't I test the chance of a false negative with Excel? What would I have to know to test a false negative?
Population.
You got it. That's exactly. I'd have to know what percentages Apple was actually using. It's easy to test if a randomizer is being random, because 10 songs should happen 10% of the time each. If I was trying to test a false negative, I'd have to know what percentage Apple was actually using, and they do not give us that kind of information wisely. You don't become a multi-million-dollar industry by giving that kind of stuff out online. Yes? Is that fair? We could track it. We could simulate it if we thought it was different. We could track it over tens if not hundreds of thousands of trials and kind of replicate the results that way. But that's why I can't do it, because I don't know what the numbers are. Is that fair? Ask me questions as you have them. This is a brand new distribution, so it's a little bit oddball. It's a little bit oddball. Teeny bit oddball. What questions do you guys have? I'm going to stop trying to read faces. I'm doing it wrong all day.
So with multiple parameters,
Go.
is all you can do test for randomness?
No! Very good question, Laura. Can you give me 20 minutes on that question? Good, good. Now, Laura just asked a fantastic question. She said, wait a minute, time out, time out. With multiple parameters, is all you can do test for randomness? No, 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 no. This is the easiest way to start. The reason it's the easiest way to start is because all the proportions have to be the same. We can test, for example, I'm going to have you guys look at flu rates across the 6 counties of Oregon. Flu rates across 6 counties of Oregon. Are they based on populations of Oregon? Is there some tie with the number of flu cases to the populations of the 6 regions? We couldn't test that for randomness because the 6 populations are not equally populated. Northwest is much more populated than Southeast. We're going to test that using M&Ms. And we'll see how that ties in after we make sure we got the... No, very good question. And no, the answer is definitely not. We can test for way more, but randomness is one nice way of testing for it. Thank you. Other questions? Good so far? So the big takeaway from this, the chi-square. Think about questions if you haven't. Shut this one down. Before we get any more. The big takeaway from chi-square is that's what the curve is going to look like. Now the curve can change depending on your degrees of freedom. When I opened up this thing, it was actually set on 4. It could be set on 50. Why is it? Oh, crap. Hang on. I know why it's not changing. It's changing up here. The curve does change with the number of degrees of freedom. For example, the example I just gave you, Laura, if we were testing from the 6 counties of Oregon, that would be 5 degrees, or 6 degrees of freedom, which would be 9. I must have erased something down here. This should be tied to it. It would look like that. If you had, for example, you were testing every county in the country at once for something, I don't know how many counties are on the country. Let's make up a number. Say it's 300. I have no idea what the actual number of counties in all the states of the country is. You would have 100 categories, and the curve actually begins to resemble a bell curve with enough categories. So like the t-distribution, this thing varies depending on how you're breaking your data down. And they're not always uniform. It's always the same percentage, like a randomness kind of algorithm. But this particular one starts with randomness. Fair enough? Fair enough. Ish. Ask me more questions if you have them. I gotta fix this spreadsheet. I want to email to myself real quick, friends. Hang on one sec. What? No, what the hell did I write it down? Now, Laura asked a fantastic question. Oh, you know what? Before we answer your question, Laura, because you guys don't carry Excel with you, mail system failure, that's fine, good. You don't carry Excel around with you yet. We're getting to that point. I did give you a program. I gave you many back in 243. I gave you sample size calc, I gave you just the normal, I gave you disk draw, I gave you disk fill. I also gave you one called GOF. And GOF at that point probably just sounded like a fun little name. It stands for goodness of fit. The reason it's called the goodness of fit is because you're trying to see how well data that you have experienced fits the distribution that you think it should fit. How well does it fit? So grab that right now. I'm going to shut this down. We're going to go to the TIs. We're going to show you how to use this bad boy. And the reason I wrote this program was, back in the day, the TI-83/84 actually came with nothing at all that could do this. And then the newer 83s and 84s began including a statistical test that could run this, but it was kind of clunky. So I decided to write one for you instead that was better. So if you go to your programs and find GOF, where this is kind of out of order. When you run GOF, it says observed list. Now right now we're going to break the program. And break meaning not a bad thing. We're going to stop the code from running temporarily. You have to make sure you've already placed your data into the TI in order to run this program. So press the on button, if you will, and you'll get an error that says quit or go. Dude, just quit. Totally fine, just quit. You're done. Press clear if you want to. What you have to do is go into your lists. This entire computation that we just did was based off of these 2 columns right here. So that's what you have to put in L1 and L2. That's what you have to put into L1 and L2. So list 1, I like to put the observes into list 1, so that's going to be 8, 3, 7, 6. We'll do a quick check, make sure I didn't screw it up. Okay, sums to 50, we're good. L2, just slap in the 5s. Sums to 50. Once you've got your observes in list 1 and your expecteds in list 2, now you can actually run. We are recording, good. We can run that program. Let's do it. Now go back to program, grab Goff. It asks, where is your observed list? Tell it L1. Second one. Where's your expected list? Tell it list 2. Press enter and it will generate exactly what you need and nothing more. Your test statistic is 9.6, just like we calculated by hand. And the chi-square test statistic is about the 38%, just like we calculated with Excel. So since you can't carry Excel around, and since I never ever want you doing this again, you can crunch it this way. It doesn't give you a graph, but you don't need to have the graph, honestly. You don't need to have the graph, because this is doing exactly the same thing for you. Decent. Same conclusions. A p-value less than 5% means something's up. A p-value bigger than 5% means nothing's up. But the important thing still is to have the null hypotheses listed in front of you. That's still the important thing. That's still the important thing. Ask the question, Jack, go.
I didn't see the buttons that you pushed.
To get. Oh, so you ran the program.
I got the
And then it says expected list or observed list. Oh, it's in the program menu, not statistics, it's in program.
Okay.
So expected list, just put in L1. No, wrong. Observed list, put in L1. Expected list, put in L2. Assuming that's the way you put it in. Press enter, and you go. You have to run the programs by pressing enter.
You get both at the same time, right?
You get one and then the other. So it'll ask for the observed list first. Your code could be corrupted, Jack. We can fix that for you. I can re-upload or re-download the program to you if you need to. Decent? Just thought of something that's gone down. Oh, some of you have, if you look in your stat tests menu, some of you actually have a chi-square goodness of fit test listed. I don't like it, and here's why. It has a slicker interface, but it asks you to put in degrees of freedom. That pisses me off a little bit, because a program should be smart enough to be able to count that itself, which is what mine does. Mine looks at your list 1, counts up how many things are in it, subtracts 1, and calls it good. Why you should have to put degree of freedom equals 9 in this is kind of beyond me. So that's why I just give you the program. Jack, is it behaving now? It's not. Let's take a look. Let's take a look. And I'm going to answer Laura's question, which is fantastic, about why can't we just test randomness. Good question, good question. Goff. Okay, it's corrupted. We'll fix that in class. Not a problem, brother, not a problem. We're not going to run it again today. So, was that? No, and this is why it's important when you break a program to not go into it. If you go into the program, it's easy to erase a line of code, which is what happened here. There's a pause or something. I gotta read it. We can fix it. Cool? So we think the iPod randomizer is still being random, which makes me question. This all goes back to what I read, Kelly, to answer your question before. I read that Apple changed the randomizer. Mm-hmm. I'm not sure they did. That's the whole point. Assuming that randomizer in that iPod Touch is the same randomizer in the iPod Shuffle, which I'm not sure if it is. Assuming it's the same, it looks random. It doesn't look not random. So maybe what Apple did, and I have no idea if this is true, is it's kind of like when doctors prescribe placebos to their patients because they know their patients are misdiagnosing themselves, and they just give them a pill. Here's a pill. Here's a pill. So take the pill, you'll feel better. I feel awesome, doc, not knowing they got a sugar pill. Now, I have data from that in your data sheet. There's actually one little set of data there that actually tests the placebo effect. Taking a pill makes you think you're doing something, therefore your mind heals itself. Maybe Apple did the same thing. Oh yeah, we fixed the randomizer. It's still doing exactly the same thing. People now think it's being less random, so they're happy. I have no idea if that's true or not. But I have never once, when I've tested the iPod in this way, gotten a small p-value, which means nothing to me, makes me think they changed the randomizer at all. It'd be a stroke of genius if it's actually happened. Stroke of genius. But I have no evidence that says it's not being random. So all the clumping that's happening is happening clumpily, randomly clumpily. New phrase. Now, however, Laura, your question. Can you test something other than randomness? Yes. Let's talk about that. Let's talk about that.